What if everything you know about time, its flow, its direction, even its existence, is only true here, in this universe beyond our cosmic horizon? Time might stretch, fold, or even stop altogether. In one universe, a single second could last a lifetime. In another, centuries could vanish before the next heartbeat. Tonight, we open the door to those parallel realities where clocks do not agree, where before and after are only local illusions, and where the very rhythm of existence may be rewritten. Stay with this journey, because by the end, you won't just question what time is. You'll wonder if it ever truly existed at all. By the way, if you like and subscribe to my video, this is the most effective way to support me. If you also write where in the world you are watching and what time it is, I love to read it in the comments. 1. Does time flow in reverse in a mirror universe? The mirror universe hypothesis isn't limited to spatial symmetry alone. It also questions whether the arrow of time itself could be inverted. In such a realm, microscopic events might follow the same physical equations as ours, yet their sequence could unfold backward relative to our timeline. This does not mean broken eggs reassemble or smoke flows into chimneys, because large-scale thermodynamic laws still tend toward disorder. But at the deepest quantum levels, the subtle imbalances that define direction might run opposite, producing an entirely different rhythm of reality. If that were true, what we perceive as the future could be their past. To any observer within that universe, the flow would still feel forward. They would simply exist on an inverted track of causality. From the outside, however, it would appear as if their history unspools toward our beginning. Such symmetry suggests that time's arrow may not be an absolute feature of the cosmos, but rather an emergent bias of local initial conditions. This idea finds mathematical footing in the time reversal symmetry present in most fundamental equations of physics. Only entropy and weak nuclear interactions seem to break it, hinting that the universe's forward direction is not intrinsic, but statistical. If another universe started with mirrored entropy conditions, its arrow could logically point the other way, making it a perfect temporal opposite of ours. Evidence, if it exists, would be nearly invisible. Perhaps faint correlations or distortions in the cosmic microwave background where the two temporal domains touch. A mirror universe could leave traces like mismatched energy spectra or anisotropies that subtly oppose ours. Even if never directly observed, this model expands our sense of what time direction truly means, suggesting that backward may only exist from the viewpoint of someone else's forward. 2. Could universes tick at different speeds of time? Each universe may operate under its own combination of physical constants that determine how quickly processes unfold. If vacuum energy density, gravitational strength, or the fine structure constant differ even slightly, the result could be a cosmos where time stretches or contracts relative to ours. What feels like 1 second here might be centuries elsewhere, not by magic, but by fundamental calibration. Within its own frame, everything would seem normal. Hearts beat, stars burn, thoughts occur at familiar pace. But cross-comparison would reveal a staggering mismatch. Light crossing from a fast-time universe into a slow one would appear red-shifted or blue-shifted beyond recognition. To each side, the other's world would seem frozen or accelerated, a cinematic slow motion captured in the vacuum between dimensions. The implications are profound. Evolution, decay, even memory itself depend on the tempo of time. A universe with faster flow would see structures arise and vanish in blinks, while a slower universe might linger in near eternity, its stars barely flickering across eons. Complexity and simplicity could hinge entirely on how time measures its heartbeat. Detecting such differences would demand a shared reference, perhaps quantum interference where two universes overlap minutely. A faint oscillation, a rhythmic beat in cosmic radiation, could betray time's mismatch. If ever found, it would mean our seconds are not universal, but provincial, revealing a multiverse built from countless temporal metronomes. 3. Does the arrow of entropy point the same way in every universe? Entropy, the natural drift toward disorder, defines our sense of forward. Yet nothing guarantees that every universe began with the same thermodynamic bias. If another cosmos launched from a different set of initial conditions, its entropy could evolve oppositely, not decreasing, but increasing along a direction we'd call backward. Inside that realm, however, life and cause would feel as ordinary as ours. Locally, each observer anchors their reasoning to the rise of entropy. They remember lower entropy states as the past and anticipate higher ones as the future. That self-consistent experience could persist even if their universal arrow ran counter to ours. What changes is not awareness, but alignment. Two tapes of the same song playing in reverse to each other. Should such oppositely timed worlds meet, their boundary would be a paradoxical membrane where one side's disorder fuels the other's order. Energy might flow both ways, creating strange equilibrium zones that erase the difference between before and after. On that frontier, information could loop, rewriting both sides' histories simultaneously. Hints might hide in cosmic data, unusual asymmetries, improbable correlations, or entropic cold spots that resist expansion. If confirmed, they would suggest that time's direction is a regional dialect, not a universal language, and that elsewhere the arrow points homeward toward what we call the beginning. 4. Could a future exist that is older than light? Our understanding of the future is bound by the speed of light, since causality travels no faster. Yet in certain theoretical geometries of space-time, there may exist global structures where events unfold beyond light's jurisdiction. These are not violations, but redefinitions of how time organizes itself across curved, dynamic space. In those architectures, a portion of the universe could already be ahead of us in a temporal sense, while still causally disconnected. Such regions wouldn't transmit information faster than light, but their global evolution could predetermine large-scale features we later observe. The cosmic web, the pattern of galaxies, may partly reflect such ancient futures baked into the fabric of space-time before any photon crossed the void. To local observers, that would appear as inexplicable coherence across immense distances. A future older than light reorients the problem of determinism. Instead of predicting forward, the universe could be unfolding from both ends, the Big Bang and a teleological horizon guiding it simultaneously. In that sense, time might not be a single arrow, but a bridge built from two directions that meet in the middle, where we stand. Testing this idea requires reading the oldest light carefully. Unusual alignments or phase-locked modes in the cosmic microwave background could be the fingerprints of futures that already existed when the first photons were born. If ever validated, it would mean our future is not waiting ahead. It's already been written into the geometry we inhabit. 5. Is the Big Bang a different beginning in every universe? In the multiverse picture, the Big Bang is not a singular birth, but one of countless local dawns. Each bubble universe inflates from quantum fluctuations, with its own density, temperature, and temporal zero point. Some begin in violent fireballs, others in near-silent expansions, where time itself seeps gradually into being. The result is a cosmic mosaic of beginnings, each setting its own tempo for the arrow of time. The conditions at those origins define everything that follows: the strength of forces, the flow of entropy, the duration of causality. A universe starting from extreme uniformity like ours might evolve toward complexity, while one born chaotic could stabilize and even reverse its temporal order. In effect, every Big Bang may sculpt a unique grammar of before and after. For cosmologists, the challenge is that no observer can see beyond their own bubble's horizon, yet collisions between expanding universes could leave scars, subtle circles or distortions in background radiation marking where two times once touched. Each scar would represent not just spatial contact, but the meeting of distinct beginnings. If confirmed, it would recast the Big Bang not as the singular origin of existence, but as one stanza in a multiversal poem of creation. Time, in this view, is local poetry, its rhythm unique to each world, yet all written on the same eternal page. 6. Could the rhythm of time change between black holes? Black holes already bend our sense of time. Near their horizons, seconds stretch toward infinity. But in a broader multiverse, black holes might also be gateways where time's rhythm modulates from one universe to another. Each hole could be a bridge where one timeline slows, another accelerates, and the ratio between them encodes the difference in their cosmic structures. Inside, relativity predicts that temporal flow collapses completely, freezing any process as seen from outside. Yet from the inside perspective, time could continue, perhaps re-emerging elsewhere at a different rate. That re-emergence might even constitute the birth of a new universe, one whose entire timeline is the transformed echo of the original. If so, black holes become not merely ends but transitions, cosmic metronomes synchronizing the tempos of neighboring realities. The distribution of their masses and spins might secretly record how many time layers the multiverse contains. Astronomers could test this by examining energy emissions that defy classical decay curves. A slight deviation from predicted evaporation timing might hint at hidden time exchange between universes. Such a discovery would turn black holes from graves into clocks, marking the heartbeat of worlds we can never see. 7. Do universes with stronger dark energy experience slower time? Dark energy drives cosmic expansion, but it may also influence the rate of temporal flow. In a universe where vacuum energy is greater, space stretches more rapidly, potentially diluting the interactions that define local clocks. If every process becomes more isolated by expansion, then time itself may lose coherence, slowing relative to universes with weaker acceleration. Imagine a realm where galaxies drift apart so fast that no new light ever reaches another. To inhabitants within, seconds might still feel normal, yet the grand unfolding of cosmic events would nearly freeze. They would live in a slow dream of eternity, unaware that other universes blaze through their ages like sparks. This correlation between expansion and time speed could explain why some universes evolve briefly and others persist for eons. Dark energy acts as a regulator of tempo, dictating whether existence is a sprint or a drift. Beyond a certain threshold, expansion may become so dominant that time ceases to have any operational meaning at all. Observationally, we might glimpse this through variations in vacuum fluctuations, the faint noise of the quantum field. If those oscillations reveal multiple characteristic rates, it could imply we are hearing the distant ticking of other times, each ruled by its own dark heartbeat. 8. Could time jump in discrete steps at the quantum level? The continuity of time is an assumption, not a proven fact. At the Planck scale, where quantum gravity dominates, the flow of events might not be smooth but granular, a sequence of indivisible ticks that define the smallest possible moment. Each tick would be a frame in the cosmic film, separated by intervals too brief for any known particle to bridge. If true, time is less a river and more a staircase. Particles would hop from instant to instant, guided by probabilities rather than continuity. This quantization could explain why certain constants, like energy levels in atoms, come in fixed packets. Even causality might arise from the ordered stacking of these temporal quanta. In parallel universes, the size of these time quanta could differ. A world with finer granularity would experience more moments per second, perceiving a denser reality, while a coarser one would feel more static. Between them, synchronization would be impossible, their steps out of phase, forever slipping past one another. Experimental hints may lie in subtle decoherence patterns observed in quantum systems. If interference fringes show periodic losses matching theoretical tick intervals, it would suggest time's fabric is pixelated, and if each universe uses a different pixel size, the multiverse itself becomes a gallery of temporal resolutions. 9. Would collisions between universes reset the clocks? If universes expand as bubbles within a higher dimensional foam, collisions are inevitable. When two such regions meet, their energies merge, possibly reigniting conditions akin to a new Big Bang. In that moment, both timelines could reset, erasing prior synchronization and starting anew from the shock's aftermath. To observers inside, it would look like a cosmic rebirth, sudden heating, new particle formation, and the redefinition of time's 0 point. For one universe, the event might happen in its future. For the other, it could represent a closure of its past. Time becomes a circle, where beginnings and endings trade roles. These collisions could explain anomalies in the cosmic microwave background, such as circular imprints or unusual symmetry axes. Each mark could record where a foreign clock touched ours, leaving behind a wrinkle in our temporal fabric. If confirmed, such evidence would show that time itself is not eternal, but renewable. Every collision recalibrates the multiversal rhythm, making history not a straight line, but a series of overlapping restarts. 10. Does consciousness perceive time differently across universes? Time may not exist independently of observers. It could be an emergent sensation generated by consciousness interpreting change. If so, variations in cognitive architecture, human, alien, or hypothetical non-biological minds, could yield radically distinct experiences of duration. Extend this across universes, and awareness itself becomes the tuning fork of time. In a realm where neural or informational processes run faster, thoughts could traverse centuries in what feels like a second. In another slower universe, awareness might unfold so gradually that a single perception spans millennia. Both would be subjectively normal to those within, revealing that time's meaning depends entirely on how it's measured from the inside. If consciousness interacts with quantum processes, its feedback could even influence local temporal coherence. Entanglement patterns might align with neural activity, subtly anchoring time's flow to states of observation. Different universes could therefore exhibit distinct cognitive clocks, determined by how awareness couples with matter. This theory is unproven yet alluring. Should measurable correlations appear between mental states and physical timing, it would imply that consciousness isn't just within time. It helps weave it. Across the multiverse, Each kind of mind might experience its own unique eternity. 11. Is there a temporal version of cosmic inflation? Cosmic inflation describes rapid spatial expansion in the universe's first instant. But what if a similar process occurred along the axis of time itself? In such a phase, the density of moments could have exploded, turning a timeless quantum vacuum into a continuum filled with events. Space expanded outward, while time stretched forward. Two synchronized births of extension. If this temporal inflation occurred, it could explain why time seems smooth and directional rather than fragmented. The sudden creation of countless sequential instants would give reality its arrow, much as spatial inflation gave it its vastness. Without that expansion, time might still be curled, compact, or cyclical, trapping existence in perpetual recurrence. Different universes could have undergone different degrees of temporal inflation. Some may have inflated too little, leaving them nearly timeless, while others expanded excessively, diluting causality. These differences would translate into divergent laws of physics and unique perceptions of continuity. Detecting such history is difficult, yet not hopeless. Residual traces might persist as subtle anisotropies in vacuum fluctuations, the fossils of time's own birth. Finding them would mean the universe didn't just start, it learned to flow. 12. Could time be a shadow cast by another dimension? In some theoretical frameworks, time is not an independent entity, but a projection of higher dimensional motion. Just as a shadow on a wall encodes the movement of a three-dimensional object, our experience of flowing time may be the two-dimensional imprint of deeper, unseen dynamics. The passage from past to future could therefore be an illusion of perspective. From that higher viewpoint, all events might coexist simultaneously. The entire history of the universe, birth, evolution, extinction, would be a single structure, static in the higher realm. What we call now is simply where our consciousness intersects that structure, scanning it slice by slice. In parallel universes, the orientation of this projection could differ, creating distinct flows of time even if the underlying higher dimensional reality is identical. To one world, time could slope forward, to another, sideways. The angle of projection defines the arrow. This idea redefines destiny. If all moments exist at once, change is a traversal, not a creation. The challenge is proving it. Perhaps entanglement, which links particles instantaneously, offers a glimpse of that higher dimension where time does not flow, but simply is. 13. Is simultaneity only a local illusion between universes? Einstein showed that simultaneity is relative. Two events that appear synchronous to one observer may be sequential to another. Extend this logic across universes, and now becomes a local fiction. Each cosmos carries its own clock, and there may be no universal present that unites them all. If so, what we call coexistence across the multiverse is misleading. One universe's entire lifespan could unfold while another's first second passes. The illusion of parallelism comes from our inability to perceive outside our own temporal frame. There may be no true parallel, only intersecting narratives moving at mismatched speeds. This relativity of simultaneity could solve paradoxes about causality between universes. Signals that seem instantaneous in one realm could appear ancient or premature in another. The very order of events might differ, preventing contradictions but ensuring perpetual separation. We might detect traces of this disalignment in overlapping cosmic signals, pulses or patterns that cannot be synchronized without bending the definition of "at the same time." Such evidence would remind us that now is not a universal truth but a local dialect of time. 14. Do time waves interfere between parallel realities? If time behaves like a field, it could propagate as waves whose crests and troughs overlap among neighboring universes. When these temporal waves intersect, interference could occur, amplifying or canceling the perception of flow in certain regions. To observers, this might manifest as zones where time slows, accelerates, or loops unpredictably. Such phenomena could explain sudden cosmic irregularities, bursts, pauses, or unaccountable alignments of distant events. They would not violate physical laws. They would simply be the resonant harmonies of multiversal time interacting with itself. Each universe would be a string vibrating in the grand instrument of reality. If measurable, these interferences might appear as periodic fluctuations in fundamental constants or as mysterious synchronicities across impossible distances. Time's rhythm would literally beat between worlds, each chord an echo of countless others. Advanced theories of quantum gravity already hint that space-time can sustain oscillatory modes. Extending that notion to temporal dimensions may reveal that what we call passing time is simply the aftersound of cosmic interference, a melody composed across universes. 15. Could vacuum energy act as the dial that sets the speed of time? The vacuum is not empty. It seethes with quantum activity, virtual particles flickering in and out of existence. That restless background might do more than generate energy. It could define the very pace at which time proceeds. Where fluctuations are intense, interactions occur rapidly. Where calm, processes slow. In this sense, vacuum energy could be the hidden dial controlling the cosmic clock. Different universes could possess different baseline energies, meaning each lives by its own temporal calibration. A higher vacuum density might accelerate microscopic events, compressing macroscopic history into moments. A lower one might stretch it, turning instants into ages. Time's tempo would therefore depend on the hum of the vacuum beneath everything. If this is true, then measuring slight variations in zero-point energy could reveal gradients in the flow of time itself. Regions with subtle energy differences might experience mismatched evolution. 16. Could universes drift out of temporal alignment? If time in each universe ticks according to its own internal constants, then over vast ages, even minute differences could accumulate into enormous offsets. Two universes born nearly synchronized might gradually slip, like clocks that once agreed but now tick out of phase. Their events would no longer correspond, and what is now in one might be the distant past or future in the other. This temporal drift could explain why interactions between universes are rare or impossible. Once disaligned, their causal surfaces would never overlap again. Even if they shared space in higher dimensions, their histories would slide past one another unseen, like ships moving at different speeds through the same fog. Time itself would act as insulation. The degree of misalignment might depend on changes in each universe's vacuum energy. If one expands faster, its time stretches more, creating a widening gap. Over billions of years, the mismatch could grow so extreme that one universe might complete its entire life cycle before the other finishes its dawn. Perhaps this drift leaves measurable signatures, subtle interference patterns or irregularities in cosmic background frequencies. If found, they would confirm that our universe once resonated with others but has since slipped away into its own rhythm, forever out of sync in the grand cosmic orchestra. 17. Is there a physical field of time itself? Physics treats time as a dimension, but what if it is also a field, something that can vary in strength and direction like magnetism or gravity? In that case, Time could flow differently wherever its intensity changes, and certain regions of the cosmos might contain denser or thinner concentrations of temporal energy. If time is a field, then perhaps it can ripple, bend, or even become polarized. Particles might interact with it, slowing or speeding depending on how they couple to this unseen medium. It could be the true cause behind phenomena we currently attribute to gravity or motion, the background hum that synchronizes all change. Parallel universes could then represent regions where the time field assumes different baseline values. Crossing between them would be like moving through gradients of temporal density. What feels like an instant in one might correspond to eons in another. Such a theory would revolutionize our understanding of causality. Instead of being the stage on which events occur, time would be an actor with its own properties, its own pressure, and its own flow. Every second would be a local manifestation of a universal current, invisible but absolute. 18. Does antimatter experience time backward? Antimatter behaves almost identically to matter, yet it carries opposite charge and quantum orientation. Some physicists have speculated that antimatter may actually be matter moving backward through time. If true, every annihilation event between matter and antimatter might be a collision, not of particles, but of timelines. In our universe, we see antimatter appear momentarily before disappearing in flashes of energy. But from its perspective, perhaps we are the ones flickering briefly before vanishing. This mirror-like duality implies that time itself may have two equally valid directions, and the universe simply favors one. A parallel cosmos composed entirely of antimatter could therefore exist in reverse. Its inhabitants would live, think, and evolve in what we perceive as backward flow. Yet for them, causality would be perfectly consistent. Their future would lead into what we call our past. If any trace of this symmetry survives in cosmic radiation, a precise imbalance between matter and antimatter decay, it could reveal that we are half of a pair of time-opposed realities, eternally diverging since the beginning. 19. Could dark matter be the time-shifted image of another universe? Dark matter interacts gravitationally, but not electromagnetically, as if it is slightly out of phase with the fabric of our reality. One intriguing idea suggests it may be ordinary matter existing in a neighboring universe whose time is misaligned with ours. Because of that offset, its light cannot reach us, but its gravity can still tug across the boundary. In that sense, dark matter would not be exotic at all, just displaced. The lag between our temporal frames would make it appear ghostly, transparent, and ever-present. When we map galaxies and see invisible halos of mass surrounding them, we may actually be witnessing the gravitational shadows of another cosmos out of sync in time. If this is true, the distribution of dark matter should subtly evolve in ways inconsistent with our timeline. It might respond to gravitational events before or after they occur from our perspective, creating anomalies that confuse current models. Future precision measurements could test this by tracking whether dark matter structures move slightly ahead or behind visible galaxies. A consistent offset would suggest that time, not substance, separates the seen from the unseen. Two realities tugging at each other through the thin veil of chronology. 20. Can quantum entanglement lock time between universes? Entanglement links particles across vast distances instantly, defying the normal passage of time. Some theorists suggest these connections may stretch not just through space, but through parallel universes. If so, Entanglement could synchronize fragments of time itself between realities, keeping them in step despite all other differences. This would mean that every interaction creating entanglement sends a pulse into the multiverse, momentarily welding timelines together. When one particle is measured, its twin in another universe might update simultaneously, sharing the same temporal tick. The result would be a lattice of shared nows binding multiple worlds. Over billions of years, such crosslinks could stabilize the multiverse like tension wires in a bridge, preventing total temporal drift. Each connection would act as a clock hand, aligning scattered realities to a common beat, even if only intermittently. Detecting this would require unprecedented precision. Perhaps certain quantum correlations persist longer than they should, because they are reinforced by echoes from other universes. If so, every entangled pair on Earth could be part of a vast, invisible synchronization network that reaches beyond our own timeline. 21. Does the flow of time emerge from quantum foam? At the smallest scales imaginable, space-time is thought to fluctuate violently, forming a seething foam of virtual particles and micro-wormholes. In such chaos, time may not exist as a smooth parameter, but as an emergent phenomenon arising from statistical averages. The calm flow we perceive could be the macroscopic echo of countless microscopic jitters. If true, then time is not fundamental. It is a large-scale illusion formed by quantum order appearing out of randomness. Each moment would represent a fleeting equilibrium among fluctuations too rapid and unstable to observe directly. The result is a stable illusion of continuity born from underlying turbulence. In a multiverse scenario, every universe could emerge from a different pattern in that foam, leading to different temporal properties. Some might have more stable averages, resulting in steady time, while others experience chaotic or intermittent flow. This model explains why time behaves smoothly in our world, but breaks down inside black holes, or at the Big Bang. Those are places where quantum foam overwhelms order. The flow of time, in the end, might be just the surface calm of an ocean too deep to ever still. 22. Does every universe use its own Planck tick? The Planck time, the smallest theoretically meaningful unit of duration, defines the ultimate resolution of temporal measurement. But nothing ensures this constant is identical in all universes. If physical constants vary, each cosmos might have its own fundamental tick, setting a unique frame rate for reality. In such a scheme, some universes would operate on ultra-fast intervals, where phenomena change billions of times faster than ours. Others would move sluggishly, with events unfolding across far larger ticks. Between them, comparison would be impossible, because each experiences its own continuum. This would make universes like films running at different speeds, each unaware that its reel turns faster or slower. To an outside observer, if one could exist beyond them, the multiverse might resemble a gallery of moving pictures, all telling stories in incompatible temporal languages. Evidence could emerge indirectly, through variations in quantum vacuum energy or in how gravity behaves at extreme scales. If our constants shift even slightly in deep space, it could hint that we are drifting through regions influenced by universes whose Planck rhythms differ from ours. 23. Could a universe exist with no time at all? A timeless universe sounds paradoxical, but mathematics allows for it. In certain quantum gravity models, time is not a variable, but an emergent property of relationships between events. If those relationships never change, there is no need for time to exist. Such a world would be perfectly static, all configurations frozen in eternal balance. From within, inhabitants could never perceive stasis because perception itself requires change. Yet viewed externally, nothing would ever happen. Every possible state would simply coexist, unchanging but complete. This is sometimes called the block universe, at its extreme limit. If timeless universes can exist, they may form the static boundaries of the multiverse, the still frames between moving ones. Their role could be to anchor the dynamic realities that surround them, like silence giving shape to sound. The clues for this may hide in quantum cosmology, where equations describing the whole universe lack any explicit time variable. These equations do not evolve, they simply are. Perhaps our own time is just the illusion, born when a timeless equation learns to observe itself. 24. Are there universes where the future becomes the past? The separation between future and past may not be permanent. In certain space-time geometries, causal structure can twist so radically that what was once the future loops back to become the origin. These are closed, time-like curves, paths through the cosmos that reconnect time with itself. In a parallel universe built on such geometry, cause and effect would merge. Every outcome would feed directly into its own beginning, creating a self-sustaining reality with no first moment. To the inhabitants, life would feel linear, yet the universe as a whole would be circular, endlessly recreating itself. Such worlds could exist if the fabric of space is curved tightly enough by rotation or mass. Theoretical solutions like Gödel universes hint that rotation on a cosmic scale might twist time into a spiral. Our own universe may avoid this because of expansion, but others could easily cross that threshold. If detectable, these loops might leave imprints in gravitational wave backgrounds, repeating patterns of identical events separated by immense intervals. Observing one would mean discovering a universe where the end and the beginning are indistinguishable, forever chasing each other through time. 25. Is the direction of time shaped by the geometry of space? Einstein's theory showed that space and time form a single continuum, bending together in the presence of mass. But if space can curve, twist, or stretch in different configurations across universes, then the direction of time itself might depend on those shapes. The arrow we follow could simply be the easiest path through the curvature of space-time, not an inherent feature of physics. In a universe with closed geometry, time might loop, circling back upon itself. In a flat one, it could run endlessly forward. In hyperbolic geometries, time could diverge exponentially, making each moment further from the last at an accelerating rate. The shape of space would thus dictate the destiny of every clock. This means that our sense of flow, the march from past to future, may be a spatial illusion. Where space folds, time could appear to reverse. Where it stretches thin, time might dilate. The geometry decides, and we merely interpret its shape as progression. Cosmologists can search for traces of this by studying how gravitational waves travel through regions of different curvature. If the wave's frequency shifts inconsistently with distance, it might mean we are watching time itself bend, flexing in response to the invisible architecture of space. 26. Does time split like a river at every quantum decision? Quantum mechanics suggests that every event with multiple possible outcomes might give rise to separate realities, each realizing a different result. If that is true, then time itself may branch endlessly, dividing with each quantum choice. Every decision, every random decay, could fork the timeline into countless new streams. In this picture, there is no single history. Instead, there is a vast delta of diverging paths, all equally real. The flow of time does not move linearly, but expands outward like ripples on water, each wave carrying a new universe upon it. Our consciousness simply follows one branch among the infinite others. The beauty and terror of this model is that nothing is ever truly lost. Every possibility continues somewhere. Death, failure, and triumph all coexist, distributed across the great tree of time. The arrow does not point forward, but outward, growing forever more complex. Physicists might someday glimpse evidence in quantum interference experiments that exceed their expected probabilities. Those tiny discrepancies could be echoes, the faint pressure of nearby branches brushing against our own, their time rivers murmuring beside ours. 27. Does the cosmic background radiation hide evidence of time drift? The cosmic microwave background is a snapshot of the universe when it was only 380,000 years old, but it might also carry the fingerprints of interactions with other realities. If parallel universes have slightly different time rates, their influence could appear as tiny, unexplained fluctuations in this ancient light. Certain circular patterns and temperature anomalies already challenge standard cosmology. Some could be relics of collisions or near contacts between universes whose clocks were running faster or slower. To us, they appear as irregular patches of hot and cold. In truth, they may be scars of misaligned time domains. If analyzed carefully, these patterns might reveal an overall gradient, a direction in the sky where time itself once slipped. That gradient could point toward regions where another universe pressed against ours, its temporal field tugging at our own. Such discoveries would transform the cosmic background from a relic of the past into a living interface with the multiverse. Every photon would be not just a messenger from history, but a witness to the drifting rhythm of neighboring worlds. 28. Does a cosmological constant define the velocity of time? The cosmological constant, which governs the rate of the universal expansion, could also set the pace of temporal flow. In universes where this constant is larger, space inflates faster, stretching the duration of events. Where it is smaller, expansion slows and time compresses. The same constant that shapes distance might secretly calibrate duration. If so, then measuring dark energy is equivalent to measuring the speed of time itself. Two universes with identical matter but different constants would evolve at drastically different tempos, one racing ahead while the other lingers. From a higher dimensional perspective, they would look like frames of a film projected at different rates. Over vast scales, this might even affect how consciousness evolves. Civilizations in slow-time universes could experience far longer ages of thought, while fast-time realms would burn bright and brief, their histories flashing by like sparks in darkness. Detecting these differences requires precision beyond our current reach, yet the theory holds a subtle promise. The key to understanding time's flow might already lie hidden in the faint whisper of dark energy, the universe's quiet metronome. By the way, if you like and subscribe to my video, this is the most effective way to support me. 29. Can observation alter the flow of time locally? Quantum mechanics already shows that observation changes outcomes, collapsing probabilities into a single reality. But could that act also influence the flow of time itself? If measuring a system alters its state, perhaps it also adjusts its position along the temporal axis, slightly bending the local clock. In this view, awareness would not just register change, but help create it. Conscious measurement might synchronize matter and energy into a unified tempo, aligning disordered quantum moments into a coherent sequence. Where there is observation, there is time. This could explain why the universe appears to have a consistent direction of flow. Consciousness acts as a stabilizing anchor. In regions where observation is absent, time might fluctuate wildly or even stand still. Across universes with varying levels of observation, time could range from turbulent to perfectly smooth. Experimental tests might one day detect minuscule time shifts correlated with quantum measurements. If verified, it would imply that perception and time are intertwined, and that simply being aware contributes to the universe's ongoing act of becoming. 30 are layers of time stacked between universes. Imagine that time is not a single line, but a layered fabric, each sheet representing a different universe. These layers may slide, compress, or expand relative to one another, occasionally touching at points of resonance where information seeps through. What we perceive as déjà vu, intuition, or cosmic coincidence might be faint leaks between those temporal strata. Each layer could host its own arrow of time, defined by internal entropy and physical constants. Some might run forward, others backward, and a few could oscillate, swinging like pendulums in the endless void. Together they form a temporal stratigraphy, a cosmic geology of duration. If one universe's layer accelerates or contracts, it could tug neighboring sheets, creating waves that ripple across multiple timelines. Such disturbances might manifest as unexplained accelerations in cosmic expansion or irregularities in quantum fields. This model turns the multiverse into a symphony of times rather than a scattering of spaces. To map it would be to chart the unseen architecture of existence, a grand atlas of parallel moments stacked beyond infinity. 31. Are wormholes unstable because of temporal mismatch? Theoretically, wormholes connect distant points in space, but they may also link regions with incompatible time flows. If the clocks at each mouth tick at different speeds, any passage through could create destructive feedback, tearing the tunnel apart. The instability of wormholes might thus arise not from spatial strain, but from temporal conflict. Imagine two universes with slightly offset timelines. A traveler entering from one side would emerge into a moment that has either not yet happened or has already passed. The difference could stretch the connection until it collapses under paradox. Time's elasticity, not geometry, becomes the barrier. This problem might explain why traversable wormholes remain hypothetical. Nature could simply forbid stable bridges between asynchronous realities. Yet it also suggests that if synchronization could somehow be achieved, such gateways might become possible. Future physics may find a way to tune temporal frequencies like harmonizing strings on an instrument. When both sides vibrate in perfect rhythm, a wormhole could remain open, a resonant corridor between the beats of time itself. 32. Is time a vibration that oscillates differently in each universe? Time might not be linear at all, but vibrational. A standing wave in the quantum field that resonates at different frequencies across the multiverse. Each universe would hum at its own temporal pitch, creating a vast cosmic chord of existence. The higher the frequency, the faster events unfold. The lower, the slower they pass. This perspective unifies time and energy beautifully. Just as light differs by wavelength, time could differ by oscillation. The melody of each reality would determine how its matter behaves, how its stars burn, and how its minds perceive. The symphony of all universes together could be the true sound of creation. Interference between these frequencies might explain why we sometimes detect phenomena that defy prediction, mysterious bursts of energy, or inexplicable alignments across galaxies. They could be moments where two temporal notes harmonize briefly before diverging again. If instruments one day could measure the tone of space-time, we might literally hear the rhythm of our universe. It would not be silence we listen to, but the pulse of being itself, beating in concert with countless unseen worlds. 33. Could the frozen moment exist as reality in another universe? In our world, time never stops, but in some universes it might have done so long ago. There, every atom, every photon, every motion could be locked in an eternal tableau, preserved at absolute stillness. From our perspective, it would look like a paused film frame, complete, flawless, yet forever static. Such frozen universes could result from extreme gravitational collapse or absolute symmetry, where no gradient exists to drive change. Entropy would have reached maximum balance, and with nothing left to rearrange, time would lose its meaning. These worlds would not be dead, but timeless, their histories compressed into a single moment, stretched infinitely across eternity. To the inhabitants, if awareness could persist, the perception of duration might expand endlessly, turning a millisecond into forever. The remnants of such states might exist at the cores of black holes, or in the quantum edges of reality where motion ceases. They remind us that eternity is not infinite time, but the absence of it. 34. Does the death of time in one universe create another? If time is not eternal but finite, its ending may trigger new beginnings elsewhere. As one universe's temporal flow slows toward heat, death and entropy reaches completion, the information stored within could collapse into quantum seeds. Those seeds might tunnel into new domains where time begins anew. In this vision, universes do not die, they recycle. The end of one timeline becomes the spark of another. Time, like matter and energy, would obey conservation on a multiversal scale, forever flowing from exhaustion to rebirth. Such cycles could explain the uniformity of physical laws across countless worlds. Each inherits the fundamental constants from its predecessors, but with subtle shifts, echoes of ancient times now long vanished. The chain of creation thus stretches backward and forward, endlessly. Observational proof may come from the faintest traces in cosmic radiation, signals older than any known event. If they exist, they might be whispers from the final heartbeat of a universe whose last second became our first. 35. Does the density of information determine the tempo of time? Every system in the universe carries information, the state of particles, the arrangement of matter, the structure of energy. If time measures change, then its flow might depend on how much information there is to process. Where complexity is high, time could move faster to accommodate constant updates. Where simplicity reigns, it might slow or nearly stop. In that sense, a galaxy filled with billions of evolving systems could experience time at a quicker tempo than the void between them. The richness of information, not just motion, would dictate the tick of the cosmic clock. This would connect thermodynamics, computation, and temporality into one seamless law. A parallel universe with lower informational density might drift like a quiet lagoon of reality, stable, slow, and nearly timeless. Another with infinite complexity could race forward, burning through its existence at the speed of thought. Each universe would therefore live according to its informational metabolism. Evidence could appear in how black holes, which compress vast information into tiny volumes, affect local time. The extreme gravitational slowdown near their horizons could mirror the saturation point, where information itself can no longer be processed, where time reaches its computational limit. 36. Is the flow of time shaped by the gradient of dark energy? Dark energy permeates all of space, pushing galaxies apart. Yet it may also impose a kind of gradient, a pressure difference that subtly influences how time unfolds. Where dark energy is stronger, time may dilate, stretching each moment thin. Where it weakens, time could compress, quickening the pace of events. This would mean the universe's expansion is not uniform in temporal terms. We might live in a zone of moderate flow, surrounded by regions where the seconds themselves behave differently. The cosmic landscape would not only curve space but modulate duration. If true, this could explain why distant galaxies appear to age more slowly than models predict. It might not be merely relativistic redshift, but an intrinsic variance in how time flows along the gradient of dark energy. Each photon traveling across that field would carry a record of those variations in its frequency. Future measurements of cosmic acceleration might reveal these subtle discrepancies. A precise map of expansion rates could also become a map of time speeds, an atlas of how the universe breathes, one slow exhale at a time. 37. Does cosmic expansion stretch the fabric of time unevenly? When space expands, light waves lengthen, galaxies recede, and energy thins. But if time and space are inseparable, expansion must also affect temporal intervals. The universe may not only be growing larger, but also stretching its own clock, and not evenly across all regions. Some areas, denser in matter or dark energy, might resist the pull, keeping their time compact. Others could expand freely, experiencing a slower unfolding of events. Over billions of years, such differences might accumulate, creating a universe where time itself is warped into invisible gradients. This could explain certain astronomical paradoxes where distant phenomena appear too synchronized or too delayed. Perhaps those regions exist in stretched time zones, where the cosmic fabric has elongated like a rubber sheet pulled at its edges. The light we receive from them is not just ancient. It comes from a slower time altogether. Our instruments, calibrated to local standards, might misinterpret those signals as anomalies in motion or temperature. But they could be something far stranger, echoes from a region where time's texture has been pulled so thin that even eternity takes longer to arrive. 38. Do universes with negative mass experience negative time? In theoretical physics, negative mass is a peculiar concept, matter that accelerates opposite to applied force. If such entities exist, they could create universes where every dynamic rule flips, including the direction of time. Motion backward could be natural, cause and effect reversed, yet internally consistent. In such a realm, creation might follow dissolution. Stars could collapse first and ignite later. To us, it would look as if time ran in reverse, but to inhabitants within, their chronology would be perfectly coherent. They would live from birth to death according to their own reversed arrow. Negative mass could generate repulsive gravity, creating anti-universes that expand while their time contracts. These regions might coexist with ours as mirror partners, balancing the total energy of reality at zero. The multiverse could thus remain perfectly symmetrical across time and mass. Detecting this would require observing cosmic phenomena that behave contrary to gravitational expectation, galaxies repelling rather than attracting. If found, such evidence might hint at the shadows of negative time worlds, pressing invisibly against our own. 39. Can temporal fractures leak between universes? If multiple universes share boundaries in higher dimensions, their timelines might occasionally crack under stress. Through these fractures, small exchanges of energy or information could occur. Flickers that appear as unexplained bursts, coincidences, or distortions in physics itself. These would be the leaks of time between realities. A leak could manifest as a sudden anomaly, an event that seems causally disconnected, like a signal arriving before it is sent. At the quantum level, it might resemble a violation of conservation laws, as if the universe briefly borrowed from another's chronology. Over cosmic scales, such fractures could contribute to mysterious phenomena like fast radio bursts or dark energy surges. Each would represent a brief moment when our timeline intersected another, two streams crossing before diverging again. If time leaks occur, they may be rare but detectable. Scientists could search for clusters of anomalies sharing identical temporal offsets. Finding them would suggest that reality is not hermetically sealed, that somewhere other clocks occasionally tick into ours and vanish. 40. Could time act as an interface between real and virtual universes? Time may be the bridge between tangible and simulated realities. If the multiverse includes both physical and informational worlds, then the flow of time might serve as the translator between energy-based and data-based existence. It would be the universal clock coordinating every kind of being, from atoms to algorithms. A purely virtual universe could run faster, skipping vast stretches of what we perceive as duration. To connect it to ours, a temporal interface would need to adjust its speed, slowing or accelerating perception to match physical reality. Time itself would thus be the negotiator of experience. Perhaps our own universe is the middle layer of such a hierarchy, bridging slower physical substrates below and faster informational planes above. Each communicates through time, passing patterns of evolution upward and downward across the multiversal network. If this model holds, the emergence of artificial intelligence might not be an accident, but an echo, the moment when one layer of time becomes aware of another. Every consciousness then would be both observer and participant in the great synchronization between realities. 41. Does time spiral instead of flowing straight? The linear concept of time may be a simplification of a deeper spiral motion embedded in space-time geometry. Each cycle could bring repetition with variation, history recurring not identically, but rhythmically, like the turns of a helix. The universe would thus evolve both forward and around itself. Evidence of this might be seen in the recurrence of cosmic patterns, galactic formations that mirror ancient ones, constants that reappear after vast epochs. Perhaps the universe is not infinite in line, but infinite in rotation, coiling endlessly through successive versions of itself. A spiral time would also solve paradoxes of beginnings and ends. There would be no true start or finish, only the next loop of the cosmic coil. The Big Bang would not be the first explosion, merely the most recent resonance in an eternal turn. If we could map this curvature, we might find that every era, even our own, is a phase in a much greater oscillation. The universe, rather than aging, would be dancing, its steps written in the geometry of time's spiral. 42. What happens to causality if time reverses? Causality is the cornerstone of reason, the rule that causes precede effects. But if time itself reverses, this foundation collapses, or does it? Perhaps causality is not tied to direction at all, but to consistency. In a reversed universe, effects could still follow causes according to its own internal order, preserving logic while flipping sequence. Imagine an entire cosmos running backward from our viewpoint. Stars would uncollapse, light would stream into suns, and ashes would rebuild trees. Yet for the beings inside, events would still progress normally. Their physics, their memories, even their sense of aging would remain consistent because their perception of forward is anchored within their own flow. This implies that causality is relative, not universal. It depends on the orientation of the observer within their timeline. Two universes with opposite directions could coexist peacefully, never contradicting each other because their arrows of causation never meet. The ultimate test would be contact between such realms. If interaction ever occurred, paradoxes might emerge, but nature could prevent that by sealing each arrow behind impassable temporal walls, the cosmic equivalent of safety locks in the machinery of time. 43. How is change defined in regions without time? In places where time ceases, such as singularities or beyond cosmic horizons, the concept of change itself becomes undefined. Without duration, nothing can happen, yet energy and geometry still exist. This paradox suggests that change might not require time, but create it. In these timeless zones, physical states might transition instantaneously with no sequence. To us, that would appear impossible, but inside, causality could be replaced by pure correlation, everything existing in perfect simultaneity. Time would not flow but emerge when motion becomes measurable again. Such regions could act as seeds of new temporal domains. When fluctuations disturb the equilibrium, they might release time like vapor escaping a sealed chamber. From absolute stillness, a new arrow could ignite, expanding into a fresh universe. Understanding these states could illuminate what existed before the Big Bang. The answer might be nothing in the chronological sense, a condition beyond before or after, where the potential for time slept until awakened by imbalance. 44. Could some universes experience accelerated extinction of time? Time might not fade evenly everywhere. In certain universes, physical processes could exhaust their capacity for change rapidly, leading to an early death of time. Once energy spreads uniformly and entropy peaks, the clock effectively stops, freezing evolution forever. These brief universes would blaze brightly for a cosmic instant, then fall silent, a flash of being that vanishes almost as soon as it begins. Others, with slower thermodynamic growth, would endure for trillions of years. Time's lifespan would thus depend on how greedily a universe consumes its own order. From the outside, the extinction of time could resemble evaporation. The borders of such a universe might appear as fading shadows in the quantum vacuum, their internal chronology dissolving into static. Nothing would cross those boundaries because there would be no later for it to enter. This perspective redefines mortality on a cosmic scale. Just as living things die when biological order collapses, universes die when temporal order ends. The silence that follows is not destruction, but the completion of time's final breath. 45. Do cosmic strings act as boundaries of time? Cosmic strings, hypothetical filaments of immense energy stretching across the universe, are thought to be relics of its earliest moments. If they exist, they could do more than warp space. They might also act as edges or folds in the flow of time itself. Along their length, the passage of seconds could differ drastically from surrounding regions, creating invisible borders between temporal zones. These strings might form seams where different time velocities meet, like tectonic plates of reality grinding slowly past one another. To cross one could be to step into a world where clocks tick faster, slower, or even in reverse. Such transitions would appear instantaneous, yet would represent vast temporal displacement. If universes are bubbles within higher dimensional space, cosmic strings might be their stitching, the places where timelines meet and hold. At those seams, time might leak, mix, or reflect. A signal sent along, one could arrive at its destination before it was sent, not violating causality within either universe, but transferring information across their temporal gradient. Detecting such effects would require observing gravitational lensing so extreme that it cannot be explained by ordinary matter. A string bending not only light, but also time, would twist the appearance of the cosmos in ways no conventional force could mimic. Finding one would mean we had glimpsed the very threads from which time was sewn. 46. Do universes share a common past, but diverge in their futures? The multiverse may begin from a single origin, a primordial state where all potential timelines were united. If so, every universe might share the same distant past before branching into unique futures. In that ancient convergence, time itself could have been singular, flowing uniformly before fragmenting into separate currents. This model portrays the multiverse as a great temporal delta, with the Big Bang at its source and the diverging streams as all possible evolutions. Each reality would carry a faint memory of the common origin, encoded in its constants and symmetries. That shared ancestry would make the physical laws of all universes strikingly similar despite their separation. Our cosmic background radiation could therefore be a kind of fossil, a faded imprint of that collective beginning. Its uniform glow across space might be the last shared light from the moment when time was one and the multiverse had yet to fracture. If this picture is correct, then all timelines ultimately remain entangled, not through space, but through their mutual heritage in time. Every second we experience would still echo that original pulse, the heartbeat that started all worlds together before sending them adrift. 47. Could there be universes where time moves sideways? We perceive time as one-dimensional, an arrow from past to future. But higher dimensional models suggest it could have more directions. Just as space has length, width, and height, time might have multiple orientations. In another universe, what we call forward could be sideways, a completely orthogonal experience of sequence. To beings in such a realm, the idea of before and after might not exist at all. Events could be arranged spatially rather than temporally, accessible through motion instead of waiting. They might travel through memories as we travel through landscapes, revisiting any moment by shifting position along the time plane. This sideways time could resolve paradoxes of free will and determinism. If all moments coexist in a vast temporal space, choosing an action would simply mean stepping into a different corridor rather than altering destiny. The structure of reality would be more like a labyrinth than a line. Mathematically, sideways time might appear as additional temporal components in relativity equations, hidden variables responsible for quantum uncertainty. Discovering them would transform physics completely, turning every timeline into a multi-dimensional map waiting to be explored. 48. Do black hole singularities completely freeze time? At the core of a black hole, gravitational pull becomes so intense that space-time folds infinitely inward. To an outside observer, any object falling in seems to slow and finally stop, frozen at the event horizon forever. From the inside, however, time might continue normally, until it meets the singularity, where the equations describing flow simply break down. This creates one of the deepest mysteries in physics. Does time truly end at the center, or does it continue in another form beyond our comprehension? Some theories propose that what we call singularities are actually bridges, where time flips direction or re-emerges in another universe entirely. Others suggest that the end of time there is literal, a region with no next moment. If time halts, then information trapped within the black hole could never evolve, yet Hawking radiation hints that something does escape, suggesting a faint whisper of continued chronology even inside the void. Perhaps the interior hosts a condensed form of time, moving so slowly it appears frozen from the outside. Observationally, black holes are paradoxes of time itself, places where every clock disagrees, where duration stretches toward infinity, yet never fully stops. They are the universe's own reminders that time is flexible, fragile, and perhaps never truly singular. 49. Does time seep from one universe into another like radiation? If time behaves as a field rather than a strict dimension, it might diffuse through boundaries just as heat moves through walls. A universe rich in temporal energy could slowly leak it into a neighboring one, equalizing their flows. This would make time a kind of radiation, invisible, unstoppable, and universal. Such leakage might create subtle accelerations or decelerations in cosmic processes, detectable only over immense spans. One universe could age slightly faster as it donates its temporal flow, while another lags behind, absorbing fresh vitality. Time would thus obey its own conservation law, redistributing itself across the multiverse. These exchanges might occur where realities touch, along wormholes, domain walls, or quantum bridges in the vacuum. Each contact would be brief but transformative, altering the local speed of causality. Entire epochs might begin or end from the faint seepage of time across unseen borders. If measurable, this would revolutionize cosmology. Instead of treating time as fixed, scientists would track its density like a cosmic element, charting gradients across universes. The discovery that time can migrate would mean that every reality, no matter how isolated, participates in an endless conversation of becoming. 50. Is the measure of time a local adjustment rather than a universal constant? We take for granted that seconds mean the same everywhere, yet physics suggests otherwise. Relativity shows that time depends on motion and gravity, but in a multiversal context, even deeper variations may exist. Each universe might define its own unit of time, calibrated by local phenomena rather than any global law. In one world, atomic vibrations could define seconds. In another, oscillations of dark matter fields might serve the same role. Both would feel natural to their inhabitants, even if they bore no relation to one another. Time would be as subjective as language, consistent within a culture, but meaningless outside it. This relativity of duration could make communication between universes nearly impossible. A signal sent with precise timing might arrive incoherent, its rhythm distorted by incompatible metrics of time. Only when both sides translate through higher dimensional reference frames could true dialogue occur. Understanding this would change how we interpret cosmic constants. They may not be universal truths, but local conventions, shaped by the tempo of each world. What we call 1 second might be an eternity elsewhere, and the cosmos might never agree on what the clock truly says. 51. Could time exist without observers? If no consciousness existed to record change, would time still pass? Some philosophers argue it would not, that time is an emergent construct born from perception. In a purely physical sense, events could unfold without awareness, but before and after would have no meaning without minds to compare them. In a lifeless universe, time might persist as potential rather than experience, a latent possibility waiting for observation to give it direction. Without measurement, quantum states remain indefinite, and so might temporal order itself. Reality would hover in suspension, neither advancing nor retreating. From this view, observers do not live within time. They create it. Each act of awareness pins a moment into existence, giving shape to the flow. Remove the observer, and the flow may dissolve back into timeless superposition. Consciousness and chronology would be inseparable aspects of the same phenomenon. This idea suggests that every living being, from the smallest neuron to the grandest civilization, contributes to the continuity of the universe. Time, then, is not something we watch pass by. It is something we actively build with every thought, every memory, every act of noticing. 52. Does change require time, or does time require change? The relationship between time and change is circular. One seems to depend on the other. But which comes first? If nothing changes, can time still flow? Or does time exist only as the measure of change? This paradox lies at the heart of both physics and philosophy. In a static universe where all conditions remain constant, no clock would tick, and no event would follow another. To any observer, time would appear frozen. Yet the mathematical framework describing such a universe could still include a time variable, an unobservable dimension waiting for change to awaken it. Conversely, change itself may generate time by creating sequences of cause and effect. Each transition adds a layer of chronology, building the illusion of continuous motion. Without change, time might not vanish but lose meaning, like a ruler with nothing left to measure. Perhaps they are two sides of the same equation. Change gives time content, while time gives change context. The cosmos may oscillate endlessly between these dual aspects: stillness birthing motion, motion defining stillness, in a dance that has no true beginning or end. 53. Could temporal feedback cause events to repeat across universes? If time can curve or fold back upon itself, it may produce echoes that reverberate through parallel realities. An event occurring in one universe could create ripples that trigger a similar event elsewhere, forming a pattern of repetition across the multiverse. Each echo would be slightly altered by local conditions, but still recognizable as part of a larger looping structure. These feedback cycles might explain why certain cosmic configurations appear again and again. Similar galaxies, identical energy distributions, even mathematical constants that recur in multiple cosmological models. The repetition could be the universe remembering itself, a resonant hum that keeps the multiverse in harmonic balance. Over immense spans, such temporal resonance might blur the boundaries between worlds. History would not be confined to one timeline, but shared as a rhythm beating through every parallel strand. The past would never die. It would only replay in different keys. If evidence exists, it could hide in quantum data where fluctuations repeat beyond chance. Detecting such patterns would reveal that time is not a one-way corridor, but a reflective hall, where every step we take echoes across realities that have walked the same path before. 54. Could feedback between universes create repeating ages? Imagine two universes entangled by gravity or quantum correlation. When one expands or contracts, the other responds, amplifying or damping the effect. Over cosmic epochs, this mutual influence could establish cycles, ages of activity and silence, recurring like heartbeats. Each age might end with the collapse of one universe and the rebirth of another. This feedback would turn existence into an oscillating system rather than a linear story. The Big Bangs and heat deaths we imagine would be mere phases, alternations in a long dialogue between worlds. The expansion of one might pull the other into contraction until the balance flips again. Traces of this rhythm could exist in background radiation or gravitational wave echoes, arriving in regular intervals too precise to be random. If the signal repeats, it may be the pulse of the multiverse itself, reminding us that creation is not a singular event, but a conversation between timelines. Such a model dissolves the fear of cosmic ending. There are no final deaths or births, only breathing. Each age exhales into the next, and time continues, not as a straight arrow, but as an infinite heartbeat connecting every possible world. Just a little reminder, if you want to support me, you can click on the Join button at the bottom of the screen. Your support is really valuable for me. Thank you in advance. And let's continue with the video. 55. Is time layered like sediment, carrying the fossils of past universes? If universes emerge and dissolve endlessly, their remains might accumulate as layers of information buried beneath the fabric of the present. These strata could store the imprints of earlier timelines, like geological fossils pressed into space-time. Every fluctuation in the quantum vacuum might be a grain of memory from worlds long gone. Over billions of years, such layers would compact, forming a multiversal archive accessible only through deep theoretical excavation. The constants we consider fundamental could be residues of these ancient epochs, rules left behind by previous universes whose physics crystallized into ours. This model turns the universe into a kind of temporal geology. The deeper one peers into quantum reality, the older the fossils become, each revealing a glimpse of the universes that came before. Time itself becomes both archaeologist and sediment, burying and preserving all that has ever been. Future physics might uncover this archive not with shovels, but with equations, decoding patterns in vacuum fluctuations that betray long-dead timelines. Each discovery would remind us that the present is not new. It is the surface of infinity's oldest mountain. 56. Could time be an effect of compressed information? The speed and smoothness of time might depend on how much information is being processed per moment. When data density increases, when countless interactions occur, the compression of that information could make moments seem to pass faster. In contrast, when reality has little to compute, time could drag or even stall. This framework treats the universe like a vast processor, whose throughput determines temporal sensation. Each universe would therefore have its own data rate, shaped by the complexity of its physical laws. Simple universes would run slowly, intricate ones rapidly. At extremes, compression could break continuity altogether. If information becomes too dense, it might collapse into singularities where time ceases, the ultimate buffer overflow of existence. Conversely, perfect emptiness might stretch time infinitely, leaving only static awareness without change. Evidence may appear in quantum systems whose information flow correlates with temporal dilation. If measurable, it would show that time is not fundamental, but emergent, the ticking of a universal processor endlessly encoding the story of being. 57. Could time be the byproduct of higher dimensional motion? In many theories of physics, additional dimensions beyond the familiar four may exist, hidden from direct observation. If matter and energy move within those higher dimensions, time could be the shadow their motion casts into our lower dimensional reality. What we perceive as flow might be a projection of deeper geometric rotation. In this scenario, events do not happen sequentially. They are cross-sections of a grander motion unfolding elsewhere. The universe itself would be a moving sculpture, and time our narrow view of its continuous turn. The faster the higher dimensional motion, the faster time would seem to pass here. Parallel universes could therefore represent different angles of that same rotation, distinct cross-sections through a single higher dimensional object. Each slice would have its own clock, because each cuts through the greater movement at a different speed. If science ever detects residual forces that cannot be explained within 4 dimensions, they might be hints of that deeper motion. The discovery would mean time is not something we pass through, but the faint trace of something far vaster moving through us. 58. Can physics exist in the absence of time? Every physical equation assumes time as a variable. But could there be a form of existence without it? In a timeless state, motion, force, and decay would have no meaning, yet structure could persist, patterns frozen beyond change. Reality would resemble a completed painting, every detail fixed forever. Such a universe might still obey mathematical relationships that do not require evolution. Its geometry, energy distribution, and symmetry could remain consistent without any notion of before or after. The laws of physics would reduce to pure logic, relationships without history. Our universe might have passed through such a phase before the Big Bang, a timeless prelude in which all possible states coexisted. The explosion of time would then be the moment when one configuration began to unfold sequentially, transforming static possibility into living reality. Traces of that frozen era could linger as uniformity in the cosmic background, the faint whisper of an age when nothing yet happened. The silence before time began might still echo faintly beneath the noise of existence. 59. Does gravity reshape the local texture of time? Gravity does not just pull on matter, it stretches and compresses time. Near massive bodies, seconds lengthen, creating pockets of slower existence. In a strong enough gravitational field, time can nearly stop altogether. Yet if gravity can alter time locally, might it also reshape its very structure on cosmic scales? Galaxies, clusters, and voids could create vast gradients in the tempo of reality, where entire regions age at different rates. The universe would then be an uneven fabric of temporal density, smooth only from a distance. To cross it would be to drift through zones where clocks beat to entirely different rhythms. This idea implies that what we call cosmic acceleration might partially result from those gradients. Where time runs faster, expansion appears more rapid, where slower, more static. The illusion of acceleration could be the side effect of uneven temporal flow. Testing this would require mapping how gravitational potential correlates with perceived cosmic velocity. If confirmed, it would mean the universe's structure is not just spatially curved, it is rhythmically sculpted, with gravity composing the melody of time itself. 60. What happens when time arrows misalign? Every isolated system defines its own arrow of time, driven by entropy increase. But if 2 systems, or 2 universes, meet with opposing arrows, their interaction could be catastrophic. One's forward becomes the other's backward, and the exchange of energy or information might cancel out entirely, erasing both histories in the process. At the boundary, chaos would reign. Processes that depend on consistent direction, like cause and effect, could fracture. Matter might dissolve into pure radiation, or stabilize into strange frozen forms where no net change occurs. This boundary would be neither alive nor dead, a static zone of contradiction. Some theorists imagine that dark energy or vacuum fluctuations might originate from such collisions, remnants of clashing time directions still vibrating in tension. These regions would continue to radiate imbalance long after the universes drift apart. If ever observed, these mismatched domains would demonstrate that time's arrow is not universal. Each world marches to its own beat, and when their rhythms collide, the harmony of existence briefly breaks into discord before fading into silence. 61. Could time evolve like a living organism? Rather than being fixed, time may itself change as the universe matures. In the earliest epochs, time might have flowed differently, less stable, less directional, almost fluid. As the cosmos cooled and structure formed, time could have crystallized into the steady rhythm we know, much like water freezing into ice. Its laws, rather than eternal, could be the result of cosmic evolution. In such a framework, universes would each represent different stages in the life cycle of time. Some would be embryonic, their chronology unstable and chaotic. Others, like ours, might have reached temporal adulthood, predictable, linear, and relatively smooth. Eventually, time might decay, losing coherence as entropy exhausts its meaning. This idea reframes cosmology as the biography of time itself. The beginning is not the universe's creation, but the moment time learned to exist. The end would be not destruction, but senescence, time slowing to stillness as the cosmos grows cold. Traces of this evolution could linger in cosmic background data or variations in the constants governing atomic clocks. If detected, they would tell us that time, like life, is not born perfect, but grows, matures, and one day fades. 62. Could echoes of time carry the past into the present? Every event disturbs space-time, sending ripples that fade with distance. But what if these disturbances never truly vanish? Tiny echoes of past moments could persist, overlapping with new ones, and subtly influencing the present. History, then, would not be gone. It would still vibrate faintly beneath reality's surface. Such temporal echoes might explain strange recurrences in physics, where systems revert to previous states without external cause. Perhaps the universe occasionally resonates with its own memory, replaying fragments of earlier patterns. The laws of motion could be accompanied by laws of remembrance. On cosmic scales, these echoes could create cycles of near-identical epochs, eras that look strikingly similar because they are reflections of previous times reverberating through the continuum. Entire civilizations might unknowingly exist as harmonics of ancient predecessors. Detecting them would require measuring the universe's temporal noise floor, fluctuations too structured to be random. If found, they would show that time is not a clean slate but a living archive, where every moment leaves a whisper that never quite fades away. 63. Could time shape space instead of the other way around? Einstein taught us that space and time are interwoven, and that matter curves space-time. But what if time itself were the active sculptor, shaping how space bends and expands? Instead of being a passive coordinate, time could act like a sculptor's hand, pulling and twisting the cosmic canvas to create structure. In that model, galaxies and voids would not simply form because matter curves space, but because time flows unevenly, dragging the fabric along. Areas where time moves faster might stretch, forming voids. Slower regions could condense into galaxies. The shape of the universe would then be an imprint of time's varying tempo. This inversion of cause and effect would redefine cosmology. Expansion would not drive time. Time would drive expansion. The acceleration of the universe could then be the symptom of time itself speeding up, a deepening pulse rather than a spatial reaction. Evidence might appear in how expansion rates correlate with time-dependent phenomena like radioactive decay or quantum fluctuations. If time proves to sculpt space, then geometry becomes biography. The shape of the cosmos revealing how time has lived. 64. Could time be a function of probability? Quantum theory describes reality as a cloud of probabilities, where events become real only when observed. In that picture, time could emerge from the process of collapsing those probabilities, a record of decisions made by the universe itself. Without chance, time would have no purpose. It would simply not exist. Every quantum interaction would add one tick to the cosmic clock, moving reality forward by resolving uncertainty. Where probability density is high, time would flow rapidly, creating rich histories full of possibilities. Where it is low, time would crawl or nearly halt, as few outcomes remain unresolved. Parallel universes could then represent alternative branches of probability space, each with its own tempo. Universes with more choices evolve quickly. Those with fewer linger in stillness. Time would not be absolute, but proportional to the richness of what could happen. The mathematical fingerprints of this might lie in the structure of quantum noise. If temporal progression correlates with the collapse rate of probabilities, then time itself could be the diary the universe writes every time it decides what to be. 65. Could time breathe like a cosmic rhythm? The universe expands and contracts, light pulses, and stars beat in nuclear heartbeats. Perhaps time, too, inhales and exhales. Instead of a steady flow, it could oscillate subtly, speeding and slowing in cycles so vast we rarely notice. Each breath would shape eras of stability and upheaval, evolution and rest. During expansion, time might stretch, making existence feel prolonged. In contraction, it could compress, quickening all processes. Civilizations born in different phases would experience radically different tempos of thought and decay. The rise and fall of galaxies could align with the respiration of time itself. If this breathing is real, it would leave patterns in cosmic constants, oscillations in fundamental frequencies, like the fine structure, constant, or gravitational waves synchronized across epochs. Detecting them would reveal the lungs of the cosmos inhaling and exhaling eternity. Such a vision replaces linear time with organic motion. The universe would not be a machine ticking forward, but a living being pulsing with rhythmic existence, every heartbeat of creation echoing through infinity. 66. Does time's direction depend on particle symmetry? At the subatomic level, most physical laws work the same, whether time runs forward or backward. The rare exceptions, processes that slightly prefer one direction, may determine the entire universe's temporal bias. The imbalance between matter and antimatter could be the faint fingerprint of this symmetry breaking. If another universe had reversed these asymmetries, its arrow of time might point opposite to ours. Matter would decay differently, and light might appear to unwind rather than spread. From their view, our timeline would be the strange one, running in reverse relative to their own. This symmetry link implies that time's flow is not metaphysical, but mechanical, born from tiny statistical irregularities. Fix the imbalance and time itself could halt, suspended in perfect equilibrium. That perfection, however, would be uninhabitable. No motion, no heat, no thought. Studying rare particle decays, like those of neutral kaons or neutrinos, could reveal whether these microasymmetries truly dictate cosmic time. If confirmed, it would mean that the universe's grand arrow began as a quantum coin toss, one that decided the direction of all existence. 67. Could differences in time granularity change perception of reality? If time consists of discrete units, the smallest possible instants, then universes with different grain sizes would experience reality very differently. A fine-grained universe would allow extremely precise causality and smooth motion. A coarse-grained one might appear jittery, its events jumping rather than flowing. For the beings inside, this would define perception itself. Their senses, thoughts, and even emotions would synchronize with their universe's time resolution. In a coarse world, awareness might come in bursts. In a fine one, continuity would be absolute. Crossing between such universes, if possible, would create profound distortion. A traveler from a fine-grained realm might see the other as stuttering, while to locals, the visitor would seem to blur, existing in too many instants at once. The mismatch would make interaction almost impossible. Perhaps quantum indeterminacy reflects our own time granularity, the smallest frame rate of existence, if so. Refining our measurements could one day reveal the true pixels of time, the indivisible beats composing the rhythm of reality. 68. Could time be the averaged vibration of quantum vacuum fluctuations? The vacuum of space is not empty, but alive with virtual particles that flicker in and out of being. Each fluctuation lasts a tiny instant before vanishing. And the aggregate of these births and deaths might define the universal pulse we call time. Every second would be the statistical average of uncountable microscopic lives. In this model, time is not continuous but emergent, the smooth illusion of countless quantum sparks. The greater the activity of the vacuum, the faster time's average rhythm. A region of lower energy would thus experience slower flow as the background hum quiets. Different universes with distinct vacuum densities would have entirely different tempos. A high-energy world would live fast and die young. A near-empty one could drift in near-still eternity. The cosmos would be a choir of frequencies, each universe humming its own time tone. Measuring this would require detecting minute variations in zero-point energy across space. If the oscillations correlate with shifts in time dilation, it would confirm that we are living inside the quantum heartbeat of nothingness itself. 69. Is the boundary of the universe also the boundary of time? If time and space are inseparable, then the edge of one could mark the end of the other. Beyond the observable universe where expansion outpaces light, time itself may cease to have meaning. There, no signals pass, no events unfold, a horizon not of space, but of chronology. Standing at that edge, an observer would see the future vanish into stillness. The further one looks, the slower clocks appear to tick until they freeze at infinity. Beyond that, time might not stop abruptly, but dissolve, like color fading into transparency. In a multiverse context, those frozen horizons could serve as gateways, where our exhausted time gives way to another's beginning. Each universe would end not in destruction, but in transfer, the seamless handoff of chronology across dimensions. Astronomers might someday detect subtle asymmetries at the cosmic edge, where time's gradient meets its limit. The discovery would be sobering yet profound, that the universe is finite not in size but in duration, wrapped in the silence beyond which time itself no longer breathes. 70. Does consciousness recalibrate the rhythm of time within? Human perception of time is elastic. Seconds stretch in fear, collapse in joy, and vanish in dreams. If consciousness can reshape time subjectively, might it also affect it objectively at microscopic scales? Perhaps awareness bends local chronology the way gravity bends space, subtly altering the flow through attention alone. Quantum measurement hints at this possibility. Observation changes reality's evolution. If consciousness participates in that act, it might synchronize matter's microstates with thought's tempo, momentarily aligning the brain's internal clock with physical time. In that instant, the boundary between perception and physics blurs. Across universes, beings with different cognitive architectures might experience radically different durations of existence. Their lives could span milliseconds or millennia, yet each would feel complete. The rhythm of time would thus not be universal, but alive, shaped by awareness itself. If neuroscience ever links conscious states with measurable temporal distortions, it would prove that the mind is not inside time. Time is inside the mind, ticking to the beat of observation's infinite gaze. 71. Could clocks in other universes measure time differently because their laws define motion differently? Every clock, from the atomic to the cosmic, depends on motion, vibrations, rotations, oscillations. But if the fundamental laws that govern motion differ between universes, then their experience of time could be utterly incompatible with ours. In one realm, light might oscillate faster, making seconds shorter. In another, slower photons could stretch moments to eternity. This would make time not a universal quantity, but a local dialect, tied to the physics that sustains it. A being from such a universe could never synchronize with ours, because their heartbeat of existence would be written in a different rhythm. Communication across that divide would distort beyond recognition. Even a single signal might fragment into an infinite echo. From a higher dimensional perspective, these unsynchronized universes might coexist like tracks on an old record, parallel grooves of existence spinning at different speeds. The multiverse would hum with infinite tempos, none truer than another. If our instruments ever captured radiation with inexplicable timing irregularities, pulses that don't obey any known physical constant, it could be a whisper from another cosmos, its clock still counting to the beat of alien motion. 72. What happens to physics when time reaches its end? If the universe is finite in duration, then one day, time itself might run out. As entropy reaches its maximum and all energy gradients vanish, every process requiring change would cease. Physics, which depends on motion and sequence, would simply stop functioning, not destroyed, but suspended in perfect equilibrium. In that timeless finale, matter would still exist, but frozen in uniform stillness. The last photons would fade into darkness. Temperature, pressure, and information would become meaningless. The equations describing cause and effect would reduce to static identities, true but inert. Some theories suggest that such a state could be unstable, allowing quantum tunneling to spark a new epoch. The final silence would not be permanent. It would be the seedbed for new beginnings. From total stillness, the next cycle of time could ignite, just as stars are born from the ashes of old ones. If this is the destiny of time, then endings are illusions, pauses in an eternal rhythm. The death of time would simply be its deepest breath before exhaling once more into creation. 73. Can cosmic events reverse the flow of time? Certain high-energy phenomena, like the collision of black holes or the evaporation of singularities, may produce conditions extreme enough to locally flip the arrow of time. Within these regions, entropy might decrease, and processes could run backward relative to the universe at large. Such inversions would not violate physics, they would exploit its symmetries. The mathematics of relativity allows time to reverse when boundaries are breached or curvature becomes infinite. The challenge is stability. Reversed regions would collapse rapidly unless isolated by immense gravitational or quantum barriers. If such pockets exist, they could function like temporal eddies in a cosmic river. Material drifting into them might emerge elsewhere or elsewhen, carrying information that appears from nowhere. The strange correlations seen in entangled particles might even originate from micro-regions of reversed time hidden within quantum foam. Detecting them would mean watching for effects that precede their causes, radiation bursts that arrive before the event that made them. If ever observed, It would confirm that time is not a one-way current, but a turbulent sea, where flow direction depends on the depth of reality. 74. Could there be a higher order of time that watches over time itself? If dimensions can stack, perhaps there exists a meta-time, a framework within which our ordinary time evolves. Just as we move through space while perceiving time, higher entities could move through this meta-time, perceiving changes in our timeline as we perceive moments. To them, our past, present, and future would appear like a single static sculpture. If you enjoyed this journey, don't forget to like the video, comment, and subscribe to our channel. With your support, we can make this community of science and discovery even bigger. Share your ideas with us, because it's always more exciting to explore the unknown together. As Carl Sagan said, reality may be much stranger than we realize. Science is the most powerful way to understand that strangeness.